So as always, I'll be recording the notes that we're going to go through today and posting it on the Google Classroom once we're all said and done. All the way down at the bottom of our Zoom class video section, down here in the Laws of Motion Part 2 video. So the notes for today, I posted them in a second tab for the Thursday notes, but they're actually the same notes that we were going over on Tuesday. It's just we're going over the last part of these notes today, the third law of motion. Sometimes I forget which button I'm looking at. I got so many going on. So, like I mentioned, Tuesday was all about the first and second laws, with the first one being that things will stay at rest or in motion until an outside force acts on them. Second law was force equals mass times acceleration. And now our third law, the third law of motion described by Isaac Newton, is the law of action and reaction. So in terms of its words or definition, the third law states that when one object exerts a force on a second object, so they come into contact in some way, the second object exerts a force on the first object that is equal in magnitude, so the same size force, and opposite in direction, so going the other way. So every time two objects interact with each other and exert forces, the first force is going to be exerted in one direction, and the force from the second object is going to be exerted equally in the opposite direction. Or, in a little bit more simple terms, for every action, every force, there is an equal and opposite reaction. So every time that you or some other object exerts a force on a substance, that other substance or object exerts a force back on you or on the original object. So this is kind of hard to explain just using words. So I'm going to go through a whole bunch of different examples today that kind of show exactly what we mean by this third law of motion. So if you want to think about one really big example, okay, that just kind of goes into more explanation that we don't really need. So if you want to think about a big example, you can think about a rocket engine, right? So rockets need to generate a lot of force to go up and out of the atmosphere. So when a rocket engine starts, it's pushing a whole bunch of exhaust backwards or down out of the engine, right? You've seen the videos of like the spaceship starting to take off, and there's all this fire and gas shooting down out of the rocket ship. It's creating this huge smoke plume from all of this stuff shooting out the back of the rocket. As all of that stuff pushes it backwards, because we have the engine pushes the exhaust backwards, the force of this exhaust getting pushed out is what pushes the engine forward or up if it's like sitting upright. So we have an opposite action compared to our initial one. So we start shooting the exhaust out backwards or out down, and that causes our rocket to start going up. So an equal and opposite reaction to our initial action. So the force of the exhaust coming out of the rocket and going down is what's causing the actual body of the rocket to go up. So rockets lift off by burning certain types of fuel. And so that fuel shoots out the bottom of the fuel tank of the rocket engine. When the burning fuel shoots out and goes down, the rocket itself moves up. So the gases that are given off by burning the fuel go down. Because the gases go down, that causes a force on the rocket to go up. So one action has an opposite reaction. The gases go down, the rocket ship goes up. You are actually experiencing the third law of motion right now. Same thing with me. I am sitting in my spinning, twisting office chair. When I sit down in my chair, my butt exerts a force against the chair, right? I'm sitting, gravity's trying to pull me down, and so I'm exerting a downward force on the chair. But the chair doesn't just collapse under me, right? There's feet and there's a little metal tube and there's a big cushion that I'm sitting on. And so the chair is exerting a force upwards against my body. And that is what's preventing me, or you, if you're sitting in a chair right now yourself, that's what's preventing us from falling to the ground. The downward force of your butt on the chair is equal to the upward force of the chair on your butt. So we have opposite forces that are acting and reacting with each other. There's a force of you on the chair and the force of the chair on you, holding you up. So these are our action and reaction forces. One of them, they're going in opposite directions, but they're equal in magnitude. So the force that you're putting on the chair is the same as the force that the chair is putting on you. Another really good example is how birds fly. So birds are very dependent on this third law of motion. Birds are able to fly through the air because they use their wings to push themselves along through the air. So you can see in this picture right here, this little animated picture, the bird's wings are going down, right? So the bird is flapping its wings. They start up here and then they go down here and then they go back and forth. And you'll notice that every time that the bird's wing flaps down, the bird itself goes up a little bit. So the birds are pushing down on the air with their wings. But when they do that, the air is exerting a force against the bird, and that is what's pushing it up. So the birds push the air down, which pushes their body up because the air is the reaction force against the bird wing. So again, opposite actions. One action, moving the wing down, creates the second reaction of the bird moving up. The wing is exerting a force on the air, and the air is exerting a force on the bird. That's what allows birds to be able to fly. The reason that we can't fly, even if you flap your arms up and down as fast as possible, is because our arms are relatively kind of straight and thin compared to a bird's wing that has like all those feathers and stuff on it. Our arms do not generate very much force against the air, right? So if you wave your arms up and down really fast, you can feel the air on your arm, right? I can feel like a little breeze as I wiggle my arm around like a crazy person on your Zoom call. And so the air is exerting force on our arm, but it's not very much force because we're not interacting with as much air compared to the bird wing right here. So again, the bird starts with its wing up here, and then when the bird uses its wing to put a downward force on the air, it causes the air to put an upward force on the bird. This action-reaction pair. We'll talk about a whole bunch more examples in just a second, but I want to pause right there and see if anybody has any questions about the third law of motion so far. It's probably the most difficult one to kind of wrap your head around. All right, I'm guessing that nobody's rushing to shout out anything, so people feel okay with this third law of motion so far. But we'll go through some more examples to kind of really show what exactly this means. So imagine that you are standing on a skateboard and it's up against like a wall, like you're outside or somewhere, or maybe in your house, although you probably shouldn't be skateboarding in your house. And so you push against the wall, right? And when you push against this wall, your force is going this direction, right? You're pushing this way. Hopefully it shows up on your screen like I'm pushing in the same direction. But you're pushing with your arms towards the wall, right? You're putting a force towards the wall. Well, what happens when you do that? You, on the skateboard, shoot off in the opposite direction, right? Because the wall pushed back on you with an equal and opposite force. So even though the wall itself didn't move, it wasn't physically like moving to push you. The reason why you and the skateboard move in the opposite direction of your push is because the wall essentially resisted your push with the same force, the same amount of force that you put on it. And so because the wall isn't going to move, it causes your skateboard to move in the opposite direction. So you push one direction on the wall, but that causes the wall to push back against you and causes you to scoot across the floor on your skateboard. Equal and opposite reactions. Same idea with if you're walking, like you're walking through your house and it's late at night and the lights are off and you don't really see, and you hit your toe against the edge of a door frame or a cabinet or something, and it hurts really bad, and you try not to curse because everybody else is asleep and you don't want to wake them up. When your toe hit that object, like let's say it was a rock that's in your house for some reason, your toe exerted a force against the rock, but the rock also exerted a force against your toe. So if you just kind of brush the rock with your toe, you might hurt a little bit. Or if you put a lot of force into the rock, that rock is going to put a lot of force back on your toe. And so when you hit your toe harder, it hurts more because more force went into damaging your foot in that case. Again, opposite reactions. Your toe was going one way and the rock stopped it and exerted a force in the other direction. So here's some other good examples. You have a balloon that's full of air, right? What happens when you release the bottom of the balloon? It shoots out of your hands, right? And starts zooming across the room. even though if you put your hand in front of the balloon, you can feel the air coming out this way. So the air is rushing down and out of the balloon, and this is what causes the balloon to move up. So it's the same general principle as the rocket engine that we were talking about earlier. The air is rushing down, which causes an opposite reaction of the balloon to go up. Equal and opposite forces. The balloon forcing the air out and down makes the air force the balloon to move up. Same thing with when you're hammering something into like a piece of wood or into the wall of your house, if you're gonna like hang some pictures. Normally, if it's a good piece of wood and a good nail, you can't just set it up and then do one swing and push the nail all the way in to the wall at one try, right? You usually have to go bam, 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 bam. And that's because as the hammer hits the nail, it's exerting a force on the nail, obviously. But the nail then also pushes back on the hammer. It exerts a force in the opposite direction onto the hammer. And so this is why, for the most part, when you're hammering stuff into a piece of wood or a piece of metal, you've got to do it multiple times because of all of these forces acting opposite to each other. One of my favorite examples that I think illustrates it really well is imagine that you're on like a boat, right? Either like a simple boat, like a canoe or a kayak that you might take out on the river, or like if your friend is renting a boat, like a speedboat or something. You're pulling up close to shore and you're ready to go step off the boat and onto the ground. Well, if you're still a little bit of ways away from the ground and the boat is still floating, what happens as you try and take that first step? You are trying to go forwards, but when you do that, it causes the boat to go backwards. So you, from your foot down here, as you step, you're putting force in kind of this direction, right? You're stepping down with your foot and back a little bit so that you can go forward. So the force of the boat on you is what will allow you to move forward because the boat is acting against your foot. But the force of your foot on the boat causes the boat to go backwards, right? So you go forwards at the same time the boat is going backwards, and more often than not, you're just going to face plant right into the water, right? So we have these opposite reactions. You go forward, but the boat goes backwards because of the third law of motion and the equal and opposite forces. All right, swimming is also a very good example. And it kind of is similar to the bird flying through the air that we were talking about earlier. So as you're swimming, as you're reaching out, you're generally bringing your arm kind of around and back through the water, right? So your arm, the force of your arm is going backwards, right? It's going behind you. As you're swimming, the arm is going out and behind you. But the water, the force of the water on your arm and your body is what pushes you forward. This is what allows you to swim from one end of the pool to the other, is because the action of you pushing the water backwards with your arm causes the reaction of you going forward through the water and across the pool. So an action results in an equal and opposite reaction. This can also happen on smaller levels as well. It doesn't have to happen on like the whole body level. So when you're playing baseball or you're watching a baseball game and a batter connects with the ball, right? They swing and they hit the ball. Obviously, the bat exerts a force on the ball, which is what causes the ball to zoom off across the field. But the ball also exerts a force on a bat, right? I don't know if you've ever hit a ball that was traveling a little bit speedily, but you can feel it in the bat, right? You hit it and it causes your bat to almost stop because of the force of the ball on the bat. Because the bat is a lot bigger than the ball, and because you are holding the ball, the bat, excuse me, and so the bat and you together are a whole lot more massive than the ball, the bat doesn't move a whole lot. Not only because the ball has a relatively low mass, but also because you're holding it in place, you're exerting a force of your own. But the ball, which is very light and doesn't have anything exerting other forces on it, zooms off into the field because of all of that force that was exerted by the bat. So the ball forces the bat to the left a little bit. So you swing around, it hits, and then the bat comes back a little bit from all that force on the ball, and the ball zooms off to the right due to the force from the bat. So equal and opposite reactions going on with each other again. I think this was supposed to move like a video and show like the kind of the apple and the cup coming together. But again, it would just show that when two objects interact with each other, they produce equal and opposite forces. So the apple, so if these two guys were traveling at like the same speed and collide, they would start traveling in the opposite direction, right? Because the apple would exert a force on the cup to cause it to start moving to the right, and the cup would exert a force on the apple that would cause it to start moving to the left. So we already talked about swimmers in the water. Another ball example, if you're like throwing the ball against a wall and then like catching it again and just like throwing and catching and throwing and catching. Or the same thing with like a bouncy ball on the ground. So if your kids are playing with balls that they can bounce on the ground and they bounce back up, the ball puts a force against the wall. So it's traveling to the wall, hits it and exerts a force in one direction, but then the wall or the floor, if you're bouncing it on the floor exerts a force in the opposite direction that makes the ball start traveling back up again. And then this is a similar to example to our boat example from earlier. So if you're going to jump off of a boat or a raft or something, then when you jump, the boat is exerting force on you, which is what allows you to get airborne and jump out of the boat. But you also put force on the boat, and that's what will cause it to kind of shoot backwards behind you if you attempt to jump or dive off of it. So you're exerting force in one direction. The boat is exerting a force on you in the opposite direction. So you jump off one way and the boat starts moving across the water in the opposite direction. So that is our third law of motion. When one object exerts a force on a second one, that second object will exert a force in the opposite direction on the first object. Whenever we have objects exerting forces, there'll always be a force in the opposite direction. That's how we can create things like rockets or birds taking off into the air, people swimming through the water, or being able to push yourself around on a skateboard. It's all due to these equal and opposite actions and reactions. So that is our third law of motion and the very final new material that we'll be covering in IPC class this term. So does anybody have any more questions, any other questions on the third law of motion and what exactly it means? All right, so your final two homework assignments for this week both have to do with these laws of motion that we've been covering all week. The question for today is a third law question, where essentially I just want you to describe a good example of the third law of motion. We went over a whole bunch of them today, so it shouldn't be too difficult. But all I want is for you to provide an example and explain why, or explain how it displays that third law of motion, that action-reaction law. And then tomorrow for your Friday assignment is another law question about how when you roll something along the ground, it doesn't keep rolling forever, but instead it eventually stops. Why is that? What's causing it to stop? This is going back, and I've mentioned a hit in here, something that we talked about during the first law of motion about why things on Earth can't keep traveling forever at the same speed and direction, how there are forces on Earth that'll cause them to slow down and stop. But that'll be the question posted tomorrow, is about what are those forces and how do they cause things to stop when they're rolling along the ground? And then, like I mentioned, next week is going to be all about the final. So I haven't fully finished it yet. But once I do, it'll be posted on Monday morning and then due on Thursday evening. So you have all week next week to finish it. And on Tuesday and Thursday, we'll be spending our class Zoom time going back and reviewing some of the material from the previous weeks and months in order to kind of help you guys if you're getting stuck on different places on the final itself. Speaking of the final, the last thing that I wanted to mention is the final will be due at the end of the day on Thursday, the 22nd. That is also when all of your remaining work in the course will be due as well. So anything that you are still missing, if you haven't turned it in by the end of the day, next Thursday, October 22nd, then it won't be able to count towards your overall grade. You'll end up getting a 0 for that assignment. So I'm putting together a list of the assignments that different people are currently missing in the various classes that I'm teaching. And I hope to send that out sometime during the day tomorrow to kind of let people know, hey, you're doing okay in this class so far, but here are a couple assignments that you're still missing from last week or from a couple weeks ago or from early in the term. That way you're able to get fully caught up and not have any of those missing assignments count against you in your final grade for the course.